Welcome, everybody. It's my pleasure to announce the Ladyzhenskaya lecture, which has now, since after the pandemic, has become somewhat of a tradition that we have one of the colloquia in the winter semester, preferably one of the first ones, as the Ladyzhenskaya lecture, and I hope we can keep this tradition for many more years. The Ladyzhenskaya lecture, this is number 14. We started, I think, soon after Ladyzhenskaya's passing away, 2004 or 5. And then there was a couple of years delay, or a couple of years of pause, and we restarted after the pandemic. And now I'm very happy to present our speaker this year, Svitlana Mayboroda from ETH Zürich. She has been until this summer presidential McKnight professor at the University of Minnesota in Minneapolis, and took up her new position as a professor of mathematics at the ETH in Zurich this fall. She's also the director of the Simon's collaboration project on wave phenomena, wave localization, which is also the title of her lecture, which is a huge multidisciplinary project involving physicists, engineers, and mathematicians. It's a huge spectrum, amazing range of subjects involved. And this also is this expertise that she's able to keep these different scientists together is also reflected by a prize that she received very recently, the U.S. National Lavatnik Award, which it's the first time that this has been awarded to a mathematician in the category of I think natural sciences, like physics, chemistry, where typically mathematicians don't get selected. At the same time, our core subject is hardcore GMT, geometric measure theory. She's one of her long-time collaborators, for instance, is Guy David. And she, in this context, she was very recently, this is fresh off the press, was the inaugural award of the Elias Stein Prize for developments in analysis. She's also won numerous other awards, such as she was also an invited speaker in the ICM in Rio. And she's also part of the MS, and I could continue a little more, but I think it's more interesting to hear her speak on wave localization. Thank you very much.
Well, first of all, it's a great pleasure to be and speak here. It's an honor. Thanks a lot for inviting me to. Thank you, Leslie. Yeah, we've been talking about it for 3 years now, I think, as I was slowly moving to Europe. So as announced, I'm going to talk about the localization of waves. It's part of the work within the Simon's collaboration. I'll mention a bit the physical background of the problem and then go into hardcore theorems. So the entire story today is going to rotate around something that we call the landscape of localization, which is in some sense a new mathematical tool, a new transformation, which allows to understand the core properties of the waves, the spectrum, the sort of density of states, the phase space picture for the eigenfunctions, the mobility agent, the localization questions, the spectral functions in a completely new sort of very precise, very crispy, both mathematical and physical way. But the tool is actually mathematical. The background comes from, what we are going to talk about is basically the behavior of waves in disorder. One of the most famous examples of this phenomenon is the Anderson localization, the discovery for which Anderson got a Nobel Prize in 1977. He discovered it around 50s, actually. And well, back then he said it has yet to receive adequate mathematical treatment, and we have to resort to the indignity of numerical simulations. We still have to sometimes, but hopefully I will convince you that a lot of progress has been done. Within our project, the physics part of it evolves around the disordered semiconductors, around the LEDs. So 99% of LEDs, which these lamps consist of, are made of indium gallium nitride. The indium gallium nitride, I'll show you on the next picture, is a very disordered semiconductor. And so the question of light propagation is one of those. The ultra-cold atoms are more of toy ground for fancy physicists, meaning that you can actually cool atoms to something like nanokelvin and observe atomic behavior in the actual realistic timescales. And then the organic semiconductors and its more topological disorder, again, I'll show you the pictures, which basically make up the cameras of your iPhones and the displays of your iPhones these days. So this is a promised picture of the indium gallium nitride semiconductor in the middle of it. Up are pictures from the Alana Spaz lab, who, by the way, has Nobel Prize as of last year. We were lucky in the same year, Hugo got Fields Medal and Alan Nobel Prize, so it was a good year for collaboration. And down you see the more of a cartoon of organic semiconductor. But the point that I'm trying to make is that at every possible scale, you see some amount of disorder. In the geometric sense, and the sense of the actual geometry of quantum layers, in the composition, which is, if you want, coefficients of UPD underline this, or potential in the Schrödinger equation, in the dielectric constant everywhere. And now you could, yeah? It's indium gallium nitride, and I think indium is, so if I'm not mistaken, gallium and nitride are respectively green and black, and red is indium. But basically the point is it's a map of, it's literally an atomic snapshot of indium gallium nitride. And indium makes it random.
But are you really seeing all the atoms?
Yes. There is about a billion of atoms in this picture.
So it's an Armstrong type?
It's atom probe tomography. It's a snapshot from Jim Speck's lab from Santa Barbara. It's atom probe tomography. It's literally every single atom. Yep. It's the reality. It's not a cartoon. It's, well, obviously, they make layered quantum.
But it claims to be a map of all the atoms in the lattice.
Yes. And if you are interested, I can show you millions of those. We have a lot of pretty pictures of these things. But yes, it's literally a picture of all the atoms, and it's a small sample.
I mean, this is still crystalline, right?
Define crystal. I mean, it's not, gallium nitride is on the crystal ground, it's on the grid, and the indium is random. So depends on what you mean by, if you mean by a crystal, the thing which is actually periodic, no.
Yeah, but the gallium nitride is. Right?
Gallium nitride is, and the indium is random in it.
How does it kind of ceramic like this, right?
How does it happen in nature? Please don't ask me. I'm a mathematician. Remember the story. But all I can tell you is that they can populate it at different percentages, and sort of part of the question is what percentage of indium is normal. So they're basically, like populating it. They're building the samples. So they're physically building, the layers. Okay, so now you could say that, the previous sample looks pretty uniform from distance, what disorder can do to a healthy LED. So let's look at it from the point of view of mathematics. We have a Schrödinger operator. These are going to be eigenfunctions of minus Laplacian plus v being a potential. If the potential is constant or there is no potential, we all know the solutions, sines and cosines. I pictured them here, but you know what sines and cosines look like. If the potential is smooth, this picture is distorted, but not so much. If, on the other hand, the potential is disordered, for example, many of the potentials that I'll be describing to you here are from the Anderson localization story. So what happens here, what you are looking at here is you take a n by n cube, chop it into, well, n by n pieces, and assign 0 and 1 on every piece, either uniformly or just 0 or 1 with certain probability. I mean, there are different probability laws here. But basically, black is 1 and gray is 0 in this picture. What happens in this case is what we refer to as localization. It's a phenomenological change in the behavior of semiconductor and the behavior of the system, in the behavior of mathematical sort of eigenmodes as well. What used to be sines and cosines become exponents. So these are exponentially decaying eigenfunctions, decaying from the small portion of the original domain. And the question is why and how, and for which disorder it happens, for which it doesn't, and which dimensions it happens, and which it doesn't, you know, and what's going on. This particular picture is, again, that of Anderson localization, although it's a big, I mean, what we actually study is a big realm of problems which are in principle devoted to waves in disordered geometric or not. And whether you think of it from the point of view of experimental physics, theoretical physics, or mathematics, there are many open problems. I mean, in mathematics, we have barely proved localization at the bottom of the spectrum. It's still not known what happens or how to prove delocalization or what happens at higher energies. And in terms of physics, both experiments and measurement of critical exponents of the relevant physical quantities is actually very difficult. So again, for the experimental side, Alan got Nobel Prize last year. So all of it is difficult. Now, why it's so hard to assess the behavior of waves as opposed to particles, let's say? Well, they do the exact opposite from both points of view. I mean, if you have a square well, for example, and you are a particle, you would be sitting in the square well and not being able to exit right or left. If you are a wave, you tunnel, so you are going to be decaying exponentially, but in principle, you still exist there. So you can exit through the barriers, just very weakly. The other side happens too. So this is my 0, 1 potential, and for the rest of the talk, I'll consciously keep bigger probability of 0 than of 1, so that you don't think that anything is confinement. It's completely percolating system, so in principle, there is nothing preventing propagation of waves except for randomness. And below, you see the fundamental state in a logarithmic scale. It's very localized. This is a logarithmic scale, so this is a severe exponential localization. So waves cannot go through. Particles can, waves cannot, and vice versa. This is the main, sort of with this idea, we presented the new object, and I'll try to give you some intuition behind it, which sort of governs the phenomenon of wave localization, as it turned out after, I don't know, by now almost 10 years of work on this, from any possible point of view. It lets you sort of put on the goggles of a wave. Because when you look at the system, you see the disordered potential, the complex geometry, the, I don't know, random coefficients, if it's on a manifold, dy-grad operator, or something like this. When a wave looks at the system, it sees something completely different. It sees a structure, and the structure is given by the hidden complex, but nonetheless perfectly organized landscape. And this landscape lets you predict both the energies and the geometric behavior, both where the eigenfunctions are going to be, what exactly is their decay rate, what exactly the pattern of their exponential decays, and what are the eigenvalues, and ultimately what is the decomposition of the phase space. So I'll see how far I managed to go today, because by now there is a big number of theorems in this, but I'll try to at least give you a snapshot of geometry, a snapshot of spectral behavior, and a snapshot of phase space decomposition. But first, sort of in very few words, what the landscape achieves, it gives you point-wise control on all eigenfunctions, so that at least you understand the behavior of the core, the behavior really in the part where they are localized. It shows the rate of the exponential decay. It sort of induces the metric, which lets you describe the pattern of the exponential decay. It predicts the energy levels. The minima of actually inverse of the landscape predict the energy levels, the eigenvalues. And you can see the level of precision on this picture. It's pretty spectacular. It gives you sort of, you can modify the Y law, and it gives you the non-asymptotic results on the integrated density of states. It gives you the non-asymptotic Y law. This is the first non-asymptotic Y law, which holds throughout the spectrum and independently of the potential. It gives the transport properties, and ultimately, well, Wigner-Weil formalism, again, depends on whether I manage to get there, but basically the decomposition of the phase space according to the system, according to the waves, which in turn deduces spectral function, joint density of states, and things like this. So let's get to mass. One of the first things that happened, and not the first, but probably one of the most powerful ones, is actually a rather a straightforward observation once you know it. Meaning, proving it is easy, but figuring it out, guessing it is hard. It turns out that the landscape, which is a solution to HU equals 1, so H is the Hamiltonian in the system, H is minus Laplacian plus V. Instead of solving for eigenfunctions and eigenvalues, instead of solving the eigenvalue problem, Laplace psi plus V psi equals E psi, what you are doing is you are solving something different. You are solving the equation HU equals 1, which has one solution, contrary to eigenvalue problem, which has infinite number of solutions. And this one solution, U, or rather its reciprocal, gives something that we refer to as an effective potential. Why? Because conjugating the initial equation, you get another one in which now V disappears completely. The initial potential disappears. 1 over U becomes the potential, so it's the reciprocal of the landscape. And the same U and 1 over U respectively gives you the metric on the manifold, essentially. If you sort of lift, I mean, it's more like weight in this dimension, but you can lift one dimension up and it will give you the metric on the manifold. So it sort of enters both as a manifold underlying the system and as a effective potential in the system. Now, in principle, you could tell me that, I changed one potential to another potential. What have I guessed? What have I gained? The deal is that the initial potential is this disordered, ununderstandable mass. And the landscape has this, or reciprocal of the landscape here, has this beautiful structure of wells and walls. It actually gives you chambers. It gives you the clear labyrinths that your wave is actually going to follow. Once again, waves do not follow the labyrinths of the original potential. The potential could be percolating and the waves would not. But if the landscape is percolating, then the waves are, and vice versa. So it's really the system viewed, it's almost as though it's really, the goggles of a wave. It's really the way the wave looks at the system. So let's look at the theorems. So this is about, actually this is Teritao's idea about how to raise the dimension. But again, this is just saying that this is a manifold in one dimension up. But back to the theorem. So let's take dy grad plus V, just for my own pleasure, because I like divergence form operators, not just Laplacian. But the point is that the localization or disorder could be in the metric A. It could be in potential V, and it could be in the structure of the domain. the geometry of the domain. And all three or each of three could give you localization. Or, so I'm not imposing any conditions. So we are taking general operator minus dy grad plus v. The only thing I'm saying is that v is positive or bounded from below. Then you could shift it just so that I have a positive operator. I'm solving for LU equals 1. L is the same as H. It's H for physicists, L for mathematicians most of the time. So I'm solving LU equals 1. I'm reversing it, so I'm working with 1 over u. And I'm cutting 1 over u. I'm cutting the effective potential at the level of energy lambda. So I have the structure of walls and wells, and I'm cutting at lambda. The point is that we're proving that the eigenfunctions are going to be contained in the wells, where 1 over u is less than lambda, and are going to decay exponentially exactly with the rate given by the metric deduced by 1 over u. So 1 over u minus lambda, positive part of it, induces a metric and a distance. And with this distance, we are going to be able to prove exponential decay. Again, there are no assumptions on the underlying potential. I mean, it just bounded. And even that doesn't have to be, but it was more straightforward to prove this way. Now, if you look at my theorem, I mean, first of all, the fact that I'm stating decay in L2 in the sense of L2 weight is a necessity because nothing promises you L infinity in this generality. But of course, morally speaking, this means that psi and gradient of psi are decaying exponentially as rho goes down. But then you could say, it's a rather global statement of exponential decay. How precise is it?
May I ask something? What's the connection with the Vidas approach to simulated annealing here?
Say it again, I'm sorry.
I mean, this looks very much like the Vidas approach to simulated annealing, right?
Not sure.
When you transform the stochastic process of simulated annealing to differential equation.
But what do you use as transformation for?
It's again, so you have V, right, and you want to minimize V.
Right.
And you do this by a stochastic process. And Vidas looked at this in the context of this diffusion operator.
We would have to talk more about it. I'm not sure it's the same thing, but we can. Yeah, it's a deep question. Yeah, let's talk about it. So to show you how precise it is, take a look at the pictures. Again, same potential as per usual. On the left-hand side, you see in log scale one of the eigenfunctions. On the right-hand side, you see the ansatz using the distance rho predicted. So on the right-hand side, there is nothing computing eigenfunction. This is just ansatz using the landscape. On the left-hand side is the actual eigenfunction. They are not identical, but they are pretty close, and this is all the way to 10 to minus 36. So this is basically, all the way down to numerical precision. And that's why it works so well for engineering purposes. I probably won't have time to talk too much about the proof. There is a sort of new uncertainty principle behind it. I will mention that this gives the composition of the physical space at this point, because since you have such a precise ansatz of exponential decay, it means that basically if you have split your system according to the landscape, then the eigenfunctions of the big system are exponentially close to the individual eigenfunctions of this decoupling, of the splitting, and so are the eigenvalues. So the moral is exactly sort of what I was trying to show from the beginning is you take the potential, you compute the landscape, you take what we call values, but this is basically, the sync of the values in the geographical sense, but these are the lines of steepest descent and things like this. And then these are the eigenfunctions. So you can see that they follow the predictions given by the landscape very precisely. Not only they are located in the individual cells given by the landscape, but they repeat it with shapes. No need to say this was not predictable based on the original potential. You just saw the potential. It's just a random grid. And this goes on. I mean, I have a movie somewhere, but this goes on for the first 200 eigenfunctions and things like this. And then as you raise energy, the system starts giving up. But again, it still follows the landscape, meaning that we know how it gives up with energy. We are looking at the energy levels. We are looking at 1 over u below E. So this becomes more and more porous. And as it becomes porous, the eigenfunctions go through, still following the landscape. So this is as far as the geometry is concerned. There are analogs of this result for magnetic potential for magnetic Schrödinger by my student Bruno Poggi, who is in Barcelona by now. There are analogs in the world of the random matrix theory. I don't want to spend too much time on it, but I will say that, well, Schrödinger is, of course, in dimension 1 at least a 3-diagonal operator. You have randomness on the diagonal and otherwise 1, 1, 1, 1, 1. In principle, all these questions, localization, delocalization, things like this are relevant in the context of random matrices, and this is a completely different part of mathematics, which also still has a lot of open problems. The conjecture is that localization, delocalization depends on the width of the band. In neither direction is it proved, but I will say that the same philosophy of being able to explain exponential decay, control exponential decay using an analog of the landscape still works. This is a joint theorem with Marcel Filoche and Terry Tao. It's a different proof, but it's morally the same idea now in the full context of random matrices. Again, it looks different, but it's sort of, morally the same message, just rewritten in the context of random matrices. Let's talk about, this is the simulations associated to it. Let's talk about the mobility edge a little bit. So one of the biggest open problems in this business is, well, one, proven delocalization, which is something no one can do as of now. But two, the belief, at least the belief of physicists, is that in dimension 1, everything all eigenfunctions are localized. That's one of the few things we can prove. In dimension 2, all eigenfunctions localized. I mean, for all energies, this is something we cannot prove. But in dimension 3, there is something called mobility edge, meaning that you have localization, 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 then mobility edge, and then from some energy on, the eigenfunctions delocalize. Of course, it's important in math, it's important in physics, because that's when your conductor-insulator transition happens. The very same year, last year, we managed for the first time measure mobility edge experimentally and predict it from the point of view of the landscape theory. So this is now in the context, the measurements are in the context of cold atoms. This is the team of Alona Spam. I will not give you painful physics details, but I will just say that for the first time, they can actually accurately measure it in physical setup. But more importantly, from the point of view of the theory, you can now view localization, delocalization transition as the percolation of this landscape-based potential. It's really true, and it's sort of amazing, to be honest, even to us who have been working with it so many years, that, again, percolation of the original potential has nothing to do with localization. I mean, it can be percolating forever, and if there is randomness, then you still localize. But percolation of the landscape does. And you can see on this picture, so in black is experimental data for the energies, which, on one side is delocalized, on the other side is localized. In the red, you see the dots given by the percolation of the landscape potential. So it's really the system viewed by the wave. It's really true that this is how the wave views your system, because the moment the landscape starts percolating, the wave actually goes through. And vice versa, while it's actually confining, it does not. which is, again, quite miraculous, because that's not what potentials do. So this is some sort of a very faithful transformation from the point of view of waves. I'll skip some probabilistic results, and I'll show you this. So not only it knows about the geometry, so far we talked mostly about the geometric properties. The landscape also knows about the spectral properties. So what you see on this picture is first what was back in the day a numerical observation that the minima of the landscape, the minima of the inverse of the landscape of 1 over u are basically multiples, dimensional multiples of eigenvalues. So you literally, again, minima of the original potential have nothing to do with eigenvalues. Well, almost, they're smaller. Meaning, you know, your minimum of the potential is 0 virtually everywhere in the entire system. The eigenvalues are, of course, not. But minima of the landscape are dimensional multiples of eigenvalues at the bottom of the spectrum. So basically, you are reading off the landscape right off where your spectrum starts and how it starts. You see the numerical computations of the precision of this result. You see the theorem by our postdocs, Shuwan and Zhang, from last year, where they're proving it. This is at the bottom of the spectrum, so this is the asymptotic result, as far as the multiples of minima go. But the landscape actually also knows the entire spectrum, not just the minima, by something that we now call the landscape law. So what you do is you first go back to original while. So the while law tells you that asymptotically, as energy goes to infinity, the integrated density of states, the number of eigenvalues below energy level E, can be predicted as the volume in the phase space. This is only true as E goes to infinity. And in particular, in the picture on the right-hand side, you see in blue the actual integrated density of states, meaning it's a step function which gains 1 every time you meet an eigenvalue. In green, you see the prediction of the classical while law. It will coincide at infinity, but it's really off at the bottom. And in red, you see something that the landscape gives by just simply blindly substituting V with 1 over u. So the first idea, you know, was almost unbelievable. I mean, since it works as a potential and it's a better potential, let's try it as a potential. And then we realized over and over with experiments that it seems to give the results not asymptotically, meaning that, you know, you have an amazing precision from the beginning to the end of the system, the red line. Problem is, you know, lovely for physicists, but how do you prove this thing? I mean, every proof of the while law, every philosophy behind while law is asymptotic, because, I mean, what do you do about while law? You count the eigenvalues on a cube, and then you approximate your domain with cubes, basically. And, you know, that's why, you know, the cubes have to be of the size 1 over square root of E, because wavelengths. And so it's true, you know, if your domain is not too bad, if it's, let's say, reasonably smooth, then as E goes to 0, to infinity, this approximation is faithful, and that's the while law. So it's morally asymptotic. It's not just factually asymptotic. It's sort of morally asymptotic. And then there are the opposite results for something that's called Lifshitz tail, which is the other asymptotic in Anderson potentials near eigenvalue 0, but also an asymptotic. And then 3-4 years after, we finally could crack it. And we proved that for every potential, for every bounded potential, one can define a counting function using the landscape. One can really use 1 over u. Instead of counting volume in the phase space, you have to count appropriately the number of boxes in the phase space. And then you have a bound from above and below on the integrated density of states from both sides with dimensional constants. Again, NCs, the constants don't depend on the domain. They don't depend on its size. They don't depend on its smoothness. They don't depend on the potential, not on its size, not on its smoothness, on nothing. Whenever this inequalities makes, whenever anything is finite in this inequality, everything else is finite, and you have a bound from above and below independently on the eigenvalue. This is the first non-asymptotic version of the while law. So one of the eigenvalues with the original V is actually also true. It's called the CLR, Liebig-Rosenblum inequalities. But the other one has a lot of counterexamples. So something like this is not only not provable, it's not true with the potential.
This is now for the infinite domain?
Yes. Well, I mean, I prove it on a finite domain with constants independent on the size of the domain. And so if your potential is such that you can count it in an infinite domain, then
yeah,
yes.
But I mean, it's a result for operator with the unbounded and bounded spectrum, right?
Both of them, yes. Yeah, yeah, either way. It's true either way. And in particular, in the context of Anderson potentials, just for the sake of the game, not only it gives you correctly the Lifshitz tails, but it gives you, for the first time, logarithmic approximation and things like this. So the best previously known precision was log-log. We are getting the upper and lower bounds that you can see up there, but in principle, nothing about the theorem is about Anderson potentials, meaning that you can fit the potential you personally prefer, and it's still going to be true. The power of it is really that it works for all potentials, and so it catches sort of both interesting phenomena at infinity, interesting phenomena at zero, and whatever else happens on the way. The only reason I'm showing corollaries for Anderson is because we end up working with these potentials. This is another example which shows that it's not necessarily about, so the previous slide showed you corollaries for Anderson potential. This is something that shows you the level of precision and how else you can use it. So this is an example from Charlie Pfefferman's paper on his uncertainty principle. If you take an operator minus Laplacian minus k over x squared, then depending on k, you're passing from bounded to unbounded spectrum. It's sort of pretty neat. So there is a particular level, there is a particular value of k in which you suddenly pass from unbounded to bounded spectrum. The while law would predict it infinitely incorrectly to start with. The while law always gives infinite one, while your system could actually be bounded. I mean, your operator could actually be bounded. So the while law is infinitely incorrect. There is something called Pfefferman-Fonck version of while law, which is exactly the content of this paper. It says that there is a transition. It actually shows that there can be transition from bounded to unbounded, but it doesn't give enough precision sort of by design. That uncertainty law doesn't give enough precision to actually say where the transition is. The landscape does it, I mean, you just explicitly, for this operator, you can just compute landscape explicitly. I wrote it here, it's just a formula, it's an ODE. So you just compute explicitly, and you see exactly the critical k, you see exactly the transition. So the moral is it sort of correctly identifies the behavior, but also correctly identifies constants somehow, which is why those pictures are so precise as a black box. This is the proof over which I probably won't be going, given the time constraints. But the last thing that I want to show you is the picture of the phase space. So basically what we discussed so far is, in some version, the landscape knows the geometry, so the x behavior, and the energies, the xi behavior, the behavior in momentum. So of course, there is a temptation to check if it knows it all, if it really knows the location of an eigenfunction, if you want, in the quantum sense in the phase space, because then you have access to all quantum observables. You can compute all operators. You know everything there is to know, basically. On the other hand, you know, like energies is a projection in one direction, x is a projection in the other direction. Of course, from the fact that you can predict two projections and plus and such exotic terms doesn't mean that you can predict what's inside. But it actually does. So the proper language for it is to talk about Wigner functions. You can see a definition over here. This is a, you take an eigenfunction psi, you produce from it something that we call Wigner function, wxc of xk. And this is basically the picture of, I mean, it's now a function of two variables, momentum and x, and it basically shows you where the eigenfunctions are located in the phase space. So it has all of the information in one block. The total integral of Wigner function is 1. The projection, I mean, integral average in k gives you psi of x squared. And integral in x gives you Fourier transform squared. So it's basically some mechanism to know everything, both about the actual eigenfunction, or you know what you can observe, and about the Fourier transform. There are many challenges about Wigner function. I mean, it's almost a probability distribution over phase space, but not quite, because it's not quite positive. It is if properly averaged, but not by itself. But for instance, it transports orthogonality. So if two eigenfunctions are orthogonal, as they tend to be, then two Wigner functions are orthogonal. And from the fact that, you know, if you think of it, if it were positive, if you think for a second that it is positive, which again, it's not far from being, you have a total integral 1 and you have orthogonality. So it means that you basically layer your phase space with eigenfunctions. So it's a complete decomposition, which sort of tells you how the operators are viewed by the spectrum of the system. And of course, if you can prove something about it, then you can go back to integrated density of states, to decay, to whatever you want, and to other quantum observables. So yeah, in particular, any operator can be represented as an integral of the Wigner function across, again, something that we call Weyl transform, but all of these are just formulas. I mean, it can be cleanly represented. Thinking about how to connect it to the landscape, I mean, the first thing you observe is how to connect it to the original potential, which is, of course, you know, energy is one of the observables. So you can write it using the Wigner function through the formula, which is sort of in the middle of the slide, as an integral of E against PDF of E. And PDF of E is sort of what you are looking for. But the problem is from the fact that two integrals are equal doesn't mean that two integrands are equal. And with V, they are definitely not, because otherwise, Weyl law would be true without asymptotics, at the very least. But now you sort of know the game. You are blindly substituting V by 1 over U and pray for the best. And so we did. And what we observed is that, indeed, the landscape, again, contrary to the original potential, gives you very carefully the location of the Wigner function, now in phase space. So what you see here in blue and red is one of the eigenfunctions, actually a sum of 10, I think. One picture is at low energy, one picture is at high energy, because it's a different physics phenomena. What you see in black, sort of in these black contour lines, are the level lines of k squared plus 1 over u equals E. So the message carried here is that the level lines of k squared plus 1 over u equals E basically tells you where the Wigner function is located. So it's going to sit within the, I mean, these black lines are the level lines of 1 over u plus k squared equals E. And basically that tells you the location of the Wigner function. And same here at low energies. These are the level lines of 1 over u plus k squared equals E for lower E, and this is the location of the Wigner function. So basically it gives you the mapping. This is more pictures and the comparison to original potential, which tells you that the original potential was bad, but probably you believe me by now. This is what you can do with the spectral function, but I'll virtually skip this. I'll just show you that on those experiments with cold atoms that Alan is running. In red, you see here the state of the art on the spectral function. So this is one of the outcomes of the Wigner function predictions. So in red, the state of the art experimental results. In green, the best prediction available before. It's semi-classical, so it's true in the semi-classical regime. As you can see going right, semi-classical means that you are shooting, well, either h to 0 or potential to infinity. So basically, the disorder is large. But in the quantum regime, the best previous prediction really had nothing to do with reality, and the landscape one is pretty much on the point. Not yet ideal, but pretty much on the point. How about proving something? Well, proving something hurts, as per usual. Wigner functions are hard. You know, while law has 100 years of history, it didn't help much, I'll be honest with you, because in the end, our proof had to be different. And again, it's a non-asymptotic phenomenon, so it's a different proof. But at least there is something to chew on. With Wigner functions, there is virtually nothing. The best available results to this date are due to Hanin and Zeldich for harmonic oscillator. So harmonic oscillator they did, you know, when Steve was still alive about 10 years ago. And the paper on more general potentials actually appeared after he passed away. But the point is, you know, they basically can do harmonic oscillators, and the potentials which have convex levels, which behave like x squared at the bottom, which behaves like x squared at the top. So basically, you know, they bark and walk as harmonic oscillators. And other than this, there is really nothing. And that's asymptotic. And we don't want asymptotic, right? And also, Wigner functions are hard by design. I mean, what I'm displaying here on the right-hand side is a Wigner function for an infinite square well. So this is just the potential given by the square well, infinite one. So the eigenfunctions are sines and cosines. You know what are sines and cosines. You know what is Fourier transform of sine and cosine. But the point is the Wigner function looks kind of complicated, even for that case. Yes, it does project onto x-axis as a sine or cosine. Yes, its Fourier transform projects, you know, essentially as a delta function, as it should. But the thing in between is not so easy to predict. And on top of it, the question is, what do you actually want? You want to prove that the thing kind of sits inside the contour of 1 over u plus xi squared equals e. What kind of means? What sit means? What inside means? I mean, like, all of this is very imprecise, right? I mean, it's physical pictures. So actually, the first conjecture came from Charlie Pfefferman. He suggested to try to prove that the mass of the Wigner function is really near this contour, in the sense that if you somehow take an appropriate circle, you know, an appropriate shell around the contour, you get, well, let's say bigger than 1/2 or bigger than 9/10. Then the number is not super important as long as it just, as long as it's a fixed number, independent on lambda and independent on things like this. And this is indeed what we, but again, remember that you want to prove that the mass is near the shell. You have two challenges. You need to prove decay outside, which is tiny bit smaller challenge, to be honest, but you also need to show that there is an annihilation inside. Because inside the contour, in L infinity, your Wigner function is huge. It's bigger than around the contour. Nonetheless, you are pretending that there is no mass. So you have to show that the oscillation cancels itself out. So outside, there is a genuine decay. Inside, there is a cancellation. So it's all really completely different from the way you think about eigenfunctions themselves. And now, well, I know the slide hurts. This is very, very fresh, so It's the right theorem, but I haven't found a crispy way to write it yet, because it's literally, a few past weeks of work. But the moral is we can prove it with not with the landscape yet, but with some very analogous construction. And this is joint work with Stefano Deccio and Jaume de Diaz, who are my postdocs, and Zhenya Malinnikova, professor at Stanford. So what we are proving is that you can define the width of the shell in terms of certain oscillations of the original potential. And then basically you can prove that what we call the excess, everything which sits outside of this shell. We are doing it in terms of print on Gaussians. It's just simpler to talk about this. But if you want, basically think of covering this contour with boxes of uncertainty principal size, appropriate boxes. And so the moral is that the Wigner function sits in the uncertainty boxes around the shell given by 1 over u plus xc squared equals e. Again, this is not yet perfectly 1 over u, but I think it's basically the way we did integrated density of states back in the day. You first do it with this potential, and then you upgrade to 1 over u. So for now, this is the best theorem we have on Wigner-Weil, but I think it already shows you, morally speaking, the location of the Wigner functions. And this hasn't been published or even written up yet, but this is the state of the art right now. OK, I'll finish here then. Thank you very much.